Hi, this is John McMaster here. Please stand by for a moment. Stream will be starting shortly. Welcome to the video, though.
Hi, I'm Ryan. I'm working out of my Los Angeles lab.
Like someone commented on my test 7 stream. Great content as always. Keep it up. I think that was test 7. Let's see. Yeah, test 7. All right, so I think we're ready. So, hi there. My name is John McMaster here in my Silicon Valley garage.
I am Ryan Quarantano, and I'm here in my Los Angeles laboratory.
All right, Ryan. What do you know about microcontroller security from the 80s? Do you know much about kind of the history there, what people would do?
Not at all. Please explain.
Okay. Well, you know about flash memory, which is used on modern microcontrollers, right?
They use floating gate transistor arrays, from what I believe.
Perfect. Do you know by chance how they erase that?
As of right now, no, I don't.
Magic electrical stuff. But did you know that there was a time before we had this black magic, and there was a few options to erase chips? Do you by chance know what those two options were? The main ones that were considered for erasing?
I know one is UV.
UV light, okay.
To erase memory, and then the other one was to probably just destroy it.
It is what?
To just destroy the chip itself.
Oh yeah, I mean that works too. That's going to erase the data. I will give you that. And let me also put a quick plug out here starting now. Yeah, X-rays was another way you can do it, but there's a lot of X-rays kind of damage the chips. So what most people did instead of X-rays is they would use UV light. And what about security? Do you know what they would do for security there?
Like
what kind of mechanisms?
Like in terms of encryption?
Yeah, like if you didn't want your code to come out of the device, what were the options there?
I guess if you wanted your code to come out of the device, encrypting the EPROM wouldn't make a difference. Actually, I'm not sure on that.
They actually did encrypt EPROMs. Some chips like the 8751 later variants did in fact have this XOR encryption. It was notable though for being pretty weak. What would happen for it was like basically like every 32 bytes, you know, you'd have like a new you repeat the XOR key. And the problem was that if you didn't use up all of your code, like say the last 32 bytes were set to FFFFF, you would just basically just expose your XOR key and yeah, so pretty weak scheme. But that was one that was pretty common.
Encrypting the EPROM wouldn't stop someone from being able to pull it out though, correct?
Well, I mean, if you were actually microprobing the EPROM itself, and depending on how they did the encryption, I mean, yeah, you could potentially do stuff. But since the EPROM is actually on die and not a discrete chip, you know, it wasn't a multi-chip module in most cases, it does make it a little bit harder to just kind of yank that out. I think one area where we did see people actually kind of more or less yanking out the EPROM was Caps Off did have the Taito C chip. And in that particular case, they were essentially yanking out the EPROM on that multi-chip module. But that's not very common. Most time it's actually on die, so you're not going to be able to just yank it out like that.
So even if you had like a programmer of some sort, it wouldn't even be able to read the EPROM because it would be encrypted.
Yeah. So taking this chip, for example, here, which is a PIC16C57, this one has some security bits, or maybe just one security bit. And I don't know if I can get better light on this, so it's easier to see. But basic idea is there's a section of EPROM memory, and possibly in that EPROM, or maybe nearby it, there tends to be a security fuse. And that security fuse controls whether if you send a read data command to the chip, whether you're going to be able to get the program memory out. So during development, you know, you'll probably keep that unprotected. But maybe at some point, what you're going to do is say, hey, lock this device. I'm sending it out, and I don't want anybody to get the code out anymore. Does that make sense so far?
Yep.
Okay. So with that in mind, what could you do to get the code out of here if you really wanted that code out anyway?
Well, I guess when you expose it to UV light, would you be like kind of trapping the charge out of the floating gates. Is that kind of the
Well, I mean, so if there's a few options, you could microprobe the security circuitry, for example. Yeah, you can use UV light, maybe just to erase that one security bit. And that was the approach that I was going to say that we're going to try today, is by shining UV light on just the security circuitry and not shining it on the main program memory. We can preserve that data in there because this is the normal process you would erase the chip with, is just bulk erasing this thing with UV light. We can get the data out. What is the issue with that though? So if I wanted the data out of here and we just blasted the whole chip with UV light, what would happen to the data we want?
you can possibly flip the bits and it just erases everything?
That's right. So how can we just hit just the security bit, assuming we knew where it was? Let's assume that we knew where it was. How could we hit just the security bit and not lose the data on the chip?
You would probably most likely want to target that one transistor or that one area that's responsible for it.
Yeah, so what are a few methods we could use to do that?
Microprogramming would be one.
Yeah, so microprobing, if we actually wanted to twiddle the actual security circuitry, what if we just want to deal with UV light? What can we do in that situation?
Would you be able to control like micro precision, the UV light, like how much of the UV light is shining down?
I've tried to do that a bit. UV optics are a bit tricky. Long story short, that tends to be difficult to do. So what people tend to do instead is actually mask all of the areas of the chip that you want to protect. Nail polish is traditional. This was not chosen very particularly, but man, I wish I had a better lighting here. Maybe I could move back a bit. Let's see. Anyways, I have just this one nail polish. It wasn't chosen for any particular reason, but just red nail polish.
You just really like
it. It's Chris Tarnowski used red nail polish, and I don't know, it's just kind of like maybe tradition, got to learn from the masters. So yeah, I use red nail polish. And yeah, so if you put this very carefully on the memory that you want to protect, then what you're going to do is you're going to end up with preserving the data, because UV light doesn't very easily pass through the nail polish. It actually gets absorbed by most materials very aggressively. That's one of the reasons why it's difficult to design UV optics. And we should get the data in the end if we know where the security bit is. Does that make sense so far?
Yeah. How do you apply enough nail polish? Like, let's say the area is so small. How do you make sure that area doesn't get nail polish on it? Like, wouldn't you
We'll show that live under a microscope. I think that's where maybe you could even say I did a little bit of innovation there to make that work smoothly. We'll get to that. I'll show you that. Okay. The last thing I'm going to say is, how do you know where the security bit is? Do you have any guesses on how you could find the security bit on here?
I have no guesses on that one.
Basically, there's two main strategies that people take. The first is die level analysis, where you say, hey, the VPP rail, that is the programming voltage rails, high voltage, it's typically not on a large portion of the chip. So it's fairly easy to say, hey, this is the programming pin. It goes to the EPROM array. Oh, and look, it goes to this other one weird place over here. Just follow that voltage rail, and that's probably the security circuitry over there, or a few related cells. That does work. It takes a little bit of analysis. The other way that you can do it, though, because that does take a bit of work, is just kind of brute force binary search. It turns out, for example, that most of the time, the security bit is not in the main EPROM array. So if all you do is just cover the main EPROM array, and then you try to do a bulk erase on the chip, there's a good chance that that security bit was not in the main EPROM array, and you'll actually deprotect the microcontroller. And so that's what we're going to do today, is we're just going to try this very naive approach to assessing where the security bit is, because we don't actually have to know where it is. We just have to know that we have enough clearance that we can protect the data that we care about. And the fact that it was somewhere else on the die, that's kind of a plus, but we actually don't need to know its exact position. Does that make sense?
So the way that you know that you got it is eventually that when you do pull, you know that you're not just pulling zeros out, or they're just like null data.
Exactly, yeah. So what we're going to do is we're going to write a test pattern to a chip, something we recognize, and then we're going to lock the chip which I just realized I may not have a good way to lock that. So I may have to run off camera for a bit, and you may have to sing a song or something while I do that. And yeah, I'm going to write some data to the chip. We're going to read it back to make sure that the data was burned to the chip correctly. And then after that, we're going to then see if we can flip the bit. And ideally, then if we unlock it, we should see the test pattern that we burned to the chip. Does that make sense?
Yep.
Cool. Okay, let me see then. I have my trusty TL866 here. This is a relatively low cost programmer. I've loaded a PIC 16C57 in here. In case it's not obvious, this chip has been decapped. That's why you're seeing the bare die there. All of the bond wires are still intact. This is not how they come from the factory. So there's many tutorials out there on decapping. So we're just going to kind of gloss over that mostly in this video. But long story short, this was nitric acid on a hot plate. And if you do that correctly, you'll keep the chip alive and expose it there. Okay, if that sounds good, let's see if there are any questions. I think David is fielding questions there, so I will continue to let him do that. Okay, what I'm going to do then is I'm going to share screen here, and I'm going to fumble through a little bit here because I didn't prepare everything. Hopefully we are going to be able to do it. So I think you can see my desktop now.
Yep, I can see your terminal.
And here, yeah, terminal. So I just have a few scripts here. And what I've prepared is the script ref.bin. It just has basically a simple counting up pattern. And it's also worth mentioning that PIC is kind of this weird architecture. You can see kind of some of the unused words there. It's actually like 12-bit or something like that words. So there's some zero padding in there. As long as we stay within the used portions of memory, we can kind of write anything you want. I just like to do this counting pattern because it's easy to see. And you can see, for example, that address E0 here corresponds to this 16-bit address here. And the reason why I did 16 bits is because, we do overflow past 8 bits. Does that make sense?
Yep. And do you know, like, from this chip where the security bit is, or are you going blind into this one?
I happen to know where this one is. I specifically chose this chip because it's well published where the security bit is. So I didn't really feel like I was, encroaching on anybody's, IP with this to a large extent because this is well published where this one is. But that aside, we're going to go through the process as if we didn't know where it was. Does that make sense?
Yeah. Don't do what I did with WCH.
Yeah. All right. So I'm just going to issue a read command, and hopefully this thing is socketed in here. And we're going to get our little thing. And I burned this earlier, I should say. So it should already be in here. Now, the only thing is I didn't actually look how to lock this. I'm realizing I should have had this. I'm hoping that we can lock this. Let's see. Do not disable write protect. Do not verify after write. Do not enable write protect. What I might be able to do then is I may fire up a VM real quick, and I may lock this. So I'll stop screen sharing, and I'm going to fire up my trusty Windows XP spyware VM. So just stand by a moment. And you're just going to probably have to trust that, that I'm going to lock it off camera. Stand by if there's any questions while I do this. Looks like so far so good. Did you hear that lovely XP startup sound? No?
No, I don't know. I'm hearing some feedback here on the.
Oh. All right. Hopefully we will have a mini pro. Stand by. Okay, I am launching the mini pro GUI. Let's see if it'll let me. It's complaining a little bit. I'm going to see if it lets me do it anyways.
Are you locking to disable automatic erase or just locking?
I'm sorry. Am I?
Are you locking?
Am I doing what?
Are you locking automatic erase or locking bits to stop people from reading the chip?
Oh yeah, I'm trying to enable a lock bit. There is a way to do it with the mini pro command line.
Yeah, so you have to create a CFG file, I believe.
Yeah, I
The
couldn't
lock,
remember the syntax. Do you
so
have that handy?
yeah, so it's just lock underscore byte, and then it can be arbitrary equal FF, XFF.
Can you paste me something in the chat?
Yeah. In the YouTube chat or Zoom chat?
Wherever, as long as I can get it.
Or I'll do YouTube. And then your config is going to look something like this.
Okay.
I don't think you need the fuses part. You just need the lock byte.
No, but I need the example of the fuse file, right?
Yeah.
Oh man, that kind of are those supposed to be on different lines?
Yeah, so fuse is low equals value, one line, fuse is high, one value, fuse is ext one value, and lock byte one value.
Okay, let me give this a try. So let me turn sharing back on over here, and we can sort this out.
That command specifically was going to do is it's going to write the configuration for fuses and lock the bits for the specified file that we were using.
Okay, so I'm going to cat this right here, and we're going to do mini pro -p pick 16 -write, and you have over here -c config.
Config.
Fuses.cfg. Does that sound about right?
Yep. And then you're going to use -e at the end, but I think E is to
Yeah,
E parameter when writing to disable automatic erase. I don't think you want that.
Well, there's no erase on this one. So let's try reading this back now, and let's see that if we get nothing back. Because if we get nothing back, it means it probably worked. Oh, I don't think that worked, unfortunately.
Okay.
Tell you what, I'm gonna do is I'm gonna turn off my camera real quick. Just stop share, and I'm gonna use a different programmer. Kind of a little bit of a delay here, but should be fine. Just stand by for a moment.
Oh, what that's doing, that's locking bits so it's locking bits specified in the file of fuses.cmd. So we just locked one. So looks like we just locked one byte.
No, it should be a global device lock. So what I'm doing is I'm going to a Windows machine that I have, and I'm going to attach my BP Microsystems programmer, which I know works with this fairly well. Now, normally I would use this laptop to do this, and this would make this a lot smoother. Unfortunately, my microscope laptop died recently, and I've been kind of working around a bunch of hardware failures and had to kind of steal it. So unfortunately, a last minute little switch there made it unavailable.
The contents of the EPROM are the contents of the flash TV.
Okay, I have plugged in the BP Microsystems programmer, powering on the system. And fingers crossed we won't have to do too many rounds of this, so this won't be too big of a delay. Okay.
We have to write the contents of the file to EPROM first before running that command.
Sorry, sorry, what's the issue there?
According to documentation, maybe we have to write the contents of the file to the EPROM before doing that. And then afterwards, you write the contents of the file to flash memory if you so wish. And then you can write the configuration for fuses and lock bits specified.
Trying to get my Windows computer to behave right now. No demo is complete without technical difficulties. Let's see. Let me think if there's something else. Otherwise, what we can do, which I would not be super happy with, but we could just show some masking demos. Let me think. Anything else I can do? It's a little disappointing. Okay, stand by. I'll have to switch to another computer. Were you able to find a alternate invocation?
Lock bit setting. Yeah, it's saying that command
So I'm doing now is I'm grabbing the solid state drive from my old programming setup, and I'm going to swap it really quick to get that computer back up. I'll be right back.
Yeah, Mike. If it has security enabled, it returns null bytes. Null bytes are just hexadecimal FF.
Okay, so I have the laptop here with the new hard drive. Guess I can turn on the video if you just want to watch me change out a hard drive. Not the most exciting, but captive audience.
Oh, I know why this might not have worked. So you have to overwrite the mini-pro.spec file that comes with your mini-pro.spec when you built your mini-pro command line tool. And then you have to use RPM dev spec tool with some.
Is this Linux year of the desktop? Is what I'm hearing.
Yeah, this is going to be Linux.
I don't think that's happening.
Really? Okay.
I think we're gonna. So it says starting Windows over here. I've got this programmer up here. I think we'll have an alternate up very shortly here, and this will probably work.
Okay. Yeah, because it's a plugin, and this guy Blurpy, who goes by the GitHub name Blurpy, made that basically allows you to do lock bits. So because you don't have that in your mini-pro.spec, it's not allowing you to lock it, or it's just not doing anything.
I see. Well, this thing is up now, so I'm just going to start BP-Win over here. And
this is definitely not.
I think we should be able to lock this shortly.
Okay.
So I don't know how much you'll be able to see there, but I'm just going to say no. Okay, I'm going to select PIC 16C57. Says blah. I'm just going to start by reading this and make sure that we get the data on here. View the buffer. I don't know how well you can see that from there, but yeah, we see our buffer here.
It's glary.
Yeah, I don't know if that's better. But just trust me anyway. So we've read this. I'm just going to save this as a backup copy just to make sure we have this over here in case we need it. If the laptop behaves. Okay. Going to create a YouTube folder. And I'm just going to call this count.bin. All right. I'm going to go over to the secure tab over here. I probably can't see it that well, but this says secure. I'm going to hit secure device. It says you are about to program this part. I'm going to say OK. It just finished securing. And I'm going to go say read back. Hit read. It says warning, device has been secured. I'm going to hit ignore to read anyway. And if I look at the buffer now, and this was something that I think David or somebody had hinted at a bit. These devices are a little bit strange. Some PIC devices, and I thought this was one that had full security. Some of them do this sort of weird XOR obfuscation-ish sort of check thing. Even though we have security enabled, it's actually giving us some data back as we try to read it. What it does is it takes the 3 nibbles and it exclusive ORs them together. So you still get some amount of your original data back. This may be a little bit hard. Why don't I get it back on my laptop and I can show you in a little more detail. So I'm taking the chip back and I'm going to put it into the Mini Pro so we can see it back on my screen over here.
Did you already confirm that you locked it?
Well, that's what I'm saying. Unfortunately, this one locking is a little bit nebulous. So what I'm going to do is I'm just going to verify that I've read it over here. Perfect. Okay, so let me share screen over here. And I've just read it back here. In fact, let me clear the screen. Now, do you remember before we basically had the address here? So this should have been, for example, something like, 1F0 or something like that, right?
Mm-hmm.
But what it's done is it's taken these 3 nibbles and it's exclusive ORed them together as kind of its like shitty protection scheme. And the idea behind this was that even if the device was locked, you would still be able to verify a device to some degree if you wanted to verify the code. Kind of like we were talking about these other XOR obfuscation schemes. So what they've done is they've taken this full value here, which was 1F0, and they've exclusive ORed the first nibble, which is 1 in this case, the second nibble, which is F in this case, and 0. So when you exclusive OR those 3 together, what do you get?
OE.
Well, you get E. So F exclusive OR 1 is E. Similarly, if we went somewhere else here, 1 exclusive OR with E is F, 1 exclusive OR with D is C. And so what we're seeing is now.
Okay.
Yeah. So
by
yeah,
the
and
address, right?
Yeah, and the full ROM, if you remember, looked more like I called it ref.bin. So we should see if we got the full data. Pardon me. If we got the full data, it should look like this. So now we know this is what an unprotected part looks like, and this is what a protected part looks like. So a little bit confusing, but just keep that in mind now as we try to do the actual analysis. Does that make sense? Okay. With that in mind then, I'm going to go over to the microscope, and now we're going to do the actual lab portion of this. Assuming I don't trip on my programmer and its power cord over the walkway. Step over this. All right. What I'm going to do now is I'm going to stop screen share and at least briefly show my equipment here. What I'm going to do is I'm going to take this bowl here, basically. And the idea is, well, let me show this first. So we've got the nail polish. Nothing too special here. Maybe I can back up, get a little better lighting, maybe. Let's see if this is a little bit better. I don't know if that's better.
Do you eventually need to remove the nail polish? Or does it matter?
We'll get to that. But depending on how good your skill is. And then what I did was I took this basically a horsehair brush. But what I've done is I've removed all but one single hair on it. I don't know if you can see the one single hair. And this gives me a very fine brush to apply the nail polish from here. The last thing though is if you just have the tip of the brush wetted, it'll dry out really quickly. So what I do to get around that is I basically take advantage of the fact that acetone dissolves nail polish, but the fumes are also very heavy. So if I squirt acetone into this bowl, it now works as sort of a shield gas. And any nail polish that I work on in here is going to maintain a very fluid viscosity, and it's not going to dry out really quickly. And then once I want the nail polish to set on the chip, I just remove it from this glass bowl here, and then it sets in place. Does that roughly make sense?
Mm-hmm.
Okay, so with that, I'm going to do is I'm going to put this under the microscope here. I'm going to put our chip in there, and then I'm going to switch over to the microscope view so we can see specifically what I'm doing to it. Just stand by. Plugging in a microscope camera. And please check if there's any YouTube questions as I'm doing this, if you can. Okay. Got a really shitty microscope feed up now. Can you see the microscope, sort of?
Yep.
Okay.
There you go.
And maybe I can take off auto exposure, maybe. This white balance is pretty awful. I don't know if that's going to get better. Let's see if we can straighten this out maybe a little.
And using your dissection microscope for this?
Yes, I am. Not a metallurgical microscope. Now, usually there is also the frame rate's a little better. I don't know why it's that, but let's turn this down a bit. We can keep zooming. Man, that white balance is not behaving, but that's okay. Okay. Let me see if I can force it to white balance, maybe. Maybe I have to hit this. Oh, there we go. Okay.
And another note, you didn't have to delayer the chip in order to do this, correct?
No, delayering it would actually hurt the chip, and we want to keep this chip fully functional.
Okay.
So not going to do that there. Now, do you by chance know what are the memory regions on this chip? Like looking at this, does anything stick out?
The bottom middle, I would say looks like a memory region.
Right here, yep.
Yep.
Okay, and there should be one other memory region. So there should be the firmware, and there should also be SRAM.
The top portion looks like it would be a memory region, if I'm not mistaken.
That's right, yeah. So one of these is SRAM, and one of them is EPROM. Do you know how to tell which one is which?
From this height? I am going to guess. Okay, I'm going to guess that the bottom might be SRAM, the top might be EEPROM.
Okay, based on what?
It's just based off me guessing.
Okay.
It's based
so
off
in my
SRAM on a bunch of chips, and it kind of looks like the SRAMs I've seen at the bottom.
Well, one thing though is when you've looked at chips, the process technology is much finer. So what happens though, if you have enough resolution, is SRAM is a much more complicated cell than EPROM. So it tends to show up with a lot more textures on dies. It may be, for example, a 6T SRAM is the classic, versus EPROM more or less, I think, is kind of like one-ish. I don't know. It's much simpler.
So SRAM would be a lot more dense, basically.
Well, it's not as much dense as it's got a lot more features. So in my experience, the rougher looking memory, I think you can see my mouse pointer here. The rougher looking memory, which would be the one at the top, tends to be the SRAM. And then the smoother looking one, the one that looks more regular, which in our case is the one at the bottom, tends to be the EPROM.
Interesting.
Similarly, we have, I think this is probably microcode right here, but we're just going to ignore that because we don't really care about how the PIC works. We only want the firmware off of it. Does that make sense?
Yes.
Cool. Okay, with that in mind, we're going to see how lucky we get that I can do this in one take. What I'm going to do now is I'm going to take the nail polish, make sure there's enough acetone in here. I think there's still plenty in here. And I'm just going to put a little bit of acetone inside the bowl itself on an object that I have there, which makes sure that, it's just, we never have to dry out the, the stylus, whatever you want to call it, as I'm moving it to work on the chip. Just keep everything in the acetone rich area. You can see right there, I've just put a blob on there. Onto this guy. Nothing magic there, just some acetone there. And then what I'm going to do is I'm going to move back to our chip. And I'm also going to rotate it a little bit just to make it a little more ergonomic to work on. Because the chip isn't decapped perfectly straight. So I just want to get access a little bit better there. Okay, and apologies, I think it looks like the table's a little bit sensitive, so I may hit this a little bit as I'm working on that. Apologies in advance for those that are going to get motion sickness. I'm just going to take the tip now of the brush and dip it into the nail polish, just so it just barely wets it. And now working under the microscope, I'm going to try to apply some on here. And I'm going to try to stick roughly in the actual EPROM area as much as possible, but not go too much further than that. So I'm using the tension of the liquid to just very gently push it out. It gives kind of a spring force. And if you do that, you actually can apply the mask finer than you can actually position it, because you're using the spring force of the wavefront to push it. So it gives you kind of a variable force as you're pushing it forward. Let's take a look at this now. Okay. Now you can see I put a mask on roughly the memory region there. I've stayed basically within the row and column circuitry. I did get a little bit messy to the right. And maybe if we really cared about this, I think you can see my mouse pointer. I might not have completely covered the EPROM right where my mouse is. But for the purposes of our demo, I'm not going to worry about that. But you see that, the EPROM memory is here. This is a little bit of the row and the column circuitry. I've bled into that a little bit. We don't really care about that. And not too much else of the die has been hit. I've hit a little bit of circuitry here. If we get unlucky, the EPROM security bit could be here, and we might have masked that. But by and large, I've mostly just hit the EPROM main memory on this die. Does that roughly make sense?
Yeah, so we like most brute forcing this, like if this doesn't work, then we take off a little bit of nail polish and then keep going from there.
Exactly, yeah. But this is just meant to be a simple demo where we shouldn't have to do too much. What I'm going to do now, though, is I'm just going to put this back in our EPROM programmer before I do anything too crazy. And we're just going to make sure that this still reads the way we think it does. I think I just shared that microscope, so I'm going to share back to desktop. And I'm going to go back to here. And I'm just going to do, I think I had something that was called like read loop or something like that. Here we go. And let's just check that. Okay, so we're still seeing this XOR pattern here. So this means this device is still locked. We're still seeing the data come back, which means this chip is still functional. So this is so far so good. What I'm going to do then is I'm going to remove this from the socket. And you can see it now here on this camera. And this is where we're going to do a little bit of black magic and a little bit less safe on the OSHA side. Now, normally what you would do is you would put this into a so-called EPROM programmer. I'm sorry, EPROM eraser. And I'm going to go over here just to show for reference what those might look like. So they might look like these type of devices here. And this is what I've been using for a long time. These might take, let's say, 10 minutes or so to erase this. And we could do that. That's just a standard sort of germicidal lamp. But in the spirit of making things quick, there's another option where you basically used high-power xenon strobe lamps, and you basically just nuke the chip with high-powered UV light. This is not entirely well understood by a lot of people, the exact mechanism this works, in terms of like how much light we're putting into this versus, you know, what is required for this lamp versus this. I think the general theory is the peak power of these lamps is a lot higher than the peak power of the conventional erasers. So by putting a relatively short burst of UV into these chips, you can erase it in a much shorter amount of time. So what I'm going to do is I'm just going to put this down here, maybe put this in a little bit of a box to avoid some amount of exposure here. I don't recommend necessarily doing this because some of the UV here, but I'm just going to do this for expediency here. So do this. And if you can hear that loud noise there, it's basically just zapping this thing with UV light. I put this down a little bit more. And I'm just going to do a few rounds of this. It has a cooldown time as I'm doing this. So I'm going to wait for it. And I'm going to do maybe 4 rounds of this. So that's number 2.
How do you know how many waves to do?
What I'll typically do is I will monitor how long it takes to bulk erase a device as a first step. Okay. What I might even do is I might even set it with the security bits, and I will see how long did it take before both the security bit and the main EPROM are erased. Because if it doesn't work in that sort of bulk erase scenario, it's also not going to work in this scenario. And that provides kind of a sanity check.
Is the point of these xenon strobes to use a shortwave UVs?
Yes, this is very powerful. So this is intended for like curing certain epoxies. And I also should say I might not have this perfectly aligned. So it may take a little bit longer depending on how well I've aligned this.
I hope you're wearing glasses.
Now this chip is now hot to the touch. Like it's been absolutely blasted with high intensity UV light at this point. I'm going to bring it over to our BP Microsystems setup, and let me see what I get here. Or, you know what? Let's get the Mini Pro set back up because I think that'll be a little better for demo purposes. Give me just a moment. And the fan volume, is that too bad, or should I turn that off?
Okay.
Okay, I can turn it off. Okay, so all I'm doing now is I've put this back in here. I'm gonna plug this back into the laptop. Let's share the screen once again. And let's go over here. Looks like it's being a little bit grumpy. Let's see what happened here. Okay, what do we got here? Ah, perfect. Okay, do you see what's happened here?
Looks like you have the unencrypted or unlocked.
That's correct, yeah. So we have successfully unlocked this device. Previously, if you recall, we were seeing the XOR of these 3 nibbles here. So this was reading, basically E here. You were seeing the XOR of these, so it was reading F here. And we actually see the upper bits of these nibbles right here. So this UV attack was basically successful. If we wanted to, we could put finer masks on the device to actually figure out exactly where the security bit is. But if you just needed some quick, proof of concept, maybe expand the mask a little bit for safety. Like I said, that corner, I was a little bit nervous about if this was something we really cared about. But by and large, you've demonstrated that an attack works. And if this was a device we really cared about, we did actually get the bulk majority of the firmware out, at least on the first try.
Nice. That looks really cool.
Yeah, so let me stop share here. Let's see. So hopefully you've been checking to see questions over here. Someone asked about particular safety glasses needed. Yeah, ideally with that UV setup, it's pointed down. So anything I'm getting right now are maybe reflections. I have it in a little bit of a box, which also helps shield things a little bit. UV is blocked by most materials. It shouldn't be too hard to make that a little bit safer with maybe a box or something to do in. I admit that it's probably okay the way it is now. But if, for example, I accidentally turned it around to look at it or something like that, that would not be ideal. So I would like to get some more long-term safeties. This is a very recent development of mine. Up until very recently, I had just been using the normal sort of way to erase these. So still a little bit of a work in progress, but results so far are quite good. So
the UV would erase the data from your eyes.
yeah, I would not look directly into this. I mean, not even cancer. I mean, this light is like really bright.
I mean, you could always coat your glasses with nail polish, to absorb
yeah,
UV.
I don't know what normal glasses are made out of. I don't know if these are soda glass or whatnot, but even if you blocked all the UV light, still bad. If you coated a nail polish, I'm not gonna be able to see anything. It'll probably do better.
Yeah, I have special UV glasses because I do have a UV light that I tried this project out one time, but it's not nearly as strong as what you have. And I took my glasses off for a split second, and man, my eyes were hurting for like maybe 12 to 15 hours.
Oh yeah.
It was brutal.
Yeah, UV exposure is no joke. One time someone also did, I think about 10 seconds, they did a TIG welding demo for me. And then I got pretty severe sunburns for about 10 seconds of TIG exposure. So yeah, remember to wear your safety equipment, kids. Someone is asking about, what's that?
I was gonna ask one more question. So
Sure.
let's say we didn't successfully unlock it. What would have been your next step? Like, what's the next step?
Well, a couple things. A lot of times what I'll do is I will kind of maybe, if I have theories for what looks like possible security circuitry, I will put several splotches down so I can test several theories at the same time. And so different masks. And then I would put them in parallel in the UV eraser because traditionally, maybe there was a 10 or 20 minute turnaround on that erasing. So it made sense to try several things at the same time. Aside from that, then if I have to remove this, originally what I was doing was something like nitric or sulfuric acid to remove this. Acetone will get most of it off, I should also say, but sometimes it clumps up a little bit. More recently, I started using this Goo Gone type stuff that's been pretty effective at just kind of bulk removing it really quickly. And I think that's what I'm going to use going forward because that actually seems to work just as well as the acids without the risk of damaging the chip. So just a quick rinse with that, and I'm able to get a clean surface to work on again.
Apparently, you can use white vinegar as well because it's very low concentration of acetic acid, and it won't damage the chip.
May work. I haven't heard of that. Sure. I would definitely want to test that though, because the vinegar aspect makes me nervous that it would damage the chip.
Yeah, I would take like maybe 2% concentrated acetic acid, like just wash it down with water and just give it a try.
Sure, give that a try.
Definitely not glacial though.
Yeah. Someone had I think there was another question there, maybe not. And hi, Mr. Peng. Let's see. Where did you get such a xenon strobe? I did a lot of research trying to figure out what would work because I had seen a lot of rumors that this type of EPROM erase existed. And I just did a lot of searching and eventually found some units on eBay that seemed to work. I even have a spare system, but it doesn't have a lamp. So I'm trying to figure out, the lamps are relatively hard to get a hold of. Unfortunately, there's not too many of these out there, and most people who are doing UV curing don't want the shortwave UV, it seems. So not particularly common. Unfortunately, I don't have a good answer. This particular system, though, the RC250B, does seem to be relatively popular. So you can find these certainly relative to most other things on eBay pretty easily, but just be aware that a lot of them don't have the lamps. And if you don't have the lamp, it's really not that interesting of a system. I also don't know if most of the ones on eBay have the shortwave UV or not. So your mileage may vary if you want to try to get one of those. Hopefully that answers that question.
Someone's asking, is it possible to pattern on some kind of mask so you get more precision with where you're masking off?
Yeah, I mean, in theory, a few other things have been suggested, like using the laser probe station. In theory, I could also etch off some masks. You could do lithography potentially to make some more precise masks. To date, nothing with that type of precision has truly been required. There is one chip, the MC68705, that because of the way the security protection works on there, if you tried to do a UV attack on that chip, you may have to do some very invasive stuff in the EPROM array where you need to get like every 8th bit or something like that in a particular area. And that you might want a pretty precise mask for that's been beyond at least what I've attempted so far. Maybe for that, it would make sense. But to date, I haven't had anything that's been problematic where I've required that. Or to put another way, if it started getting to that point where I would require these really precise masks, it might be easier for me at that point just to go to microprobing or something like that and just try a different approach. Because there are alternatives. The main advantage to this, as you just saw, is it's pretty low cost to do and fairly quick. So, it's not uncommon that a microcontroller of this security class, if someone wants me to develop an attack for, I can turn that around in about an hour. So pretty easy to develop. It just happens to be easy as long as the chip is easy.
Yeah, I was gonna say if you can develop basically something that has like the precision of a laser almost, but it's like a UV. It can become so small, so small that can like attack individual transistors at a time or individual cells at a time.
Sorry, with a laser?
With a laser, but it's like shooting UV.
Yeah, unfortunately, 250 nanometer lasers are a little bit rare and expensive. The fundamental issue is the optics or crystals used to make those are hydroscopic. So even when they get onto the surplus market, it's common for them to kind of die over time.
Okay.
Let's see if there's any other questions. Qcon is just nasty brake parts cleaner. That may be, I don't know. It's just nasty. I don't know if brake parts cleaner is more corrosive or not. I don't have a lot of experience with that. Part of the reason why I know this Gugon stuff works is that, I kind of qualified that it wasn't destroying parts. Brake parts cleaner might just work fine as well. Let's see. Dave is also mentioning other masking compounds. You can use electrical tape. That works too. Many options. I just happen to like this because, if I put the mask down, I kind of verify it's there. It's solid. It doesn't move around. With tape or something like that, it's harder to see what's kind of underneath it. I can imagine the tape maybe could slip or maybe it's not down as well as you think it is. I just happen to prefer this because it's very clear where the mask boundaries are. But sure, other methods work too. Let's see. I think those are the questions. Does anyone have any other questions? Or Ryan, do you have anything else to add?
Oh, this is great. I actually learned a lot from this. I kind of want to try this myself now.
Yeah. Let's see. The chat is still going there, but I think that's all I have. So I'm probably going to end the stream unless anyone has any other last closing thoughts. Maybe do last call, sit here for a few seconds. I think that is it. Well, thank you everyone for joining us. Thank you, Ryan.
Yeah, thank you.
And I guess see everyone next time, and everyone have a good night.